All right, good afternoon. Class here, section 1, angles and their measurements. We are looking at pre-calculus, trigonometry, chapter 5, trigonometric functions. As mentioned before, you have access to this PowerPoint, and we got to take it from there. All right, so we are going to cover 5.1 angles and their measure, and here's the objectives. Convert between decimals and degrees, minutes, seconds, measures for angles. Find the length of an arc of a circle. Convert from degrees to radians, and from radians to degrees. Find the area of a sector of a circle. Find the linear speed of an object traveling in circular motion. So those are the ones that we're going to cover for this section. First, I want to remind you before this what came, and just in case if anybody is interested. Exponential functions are in the form of f of x equals a to the power of x, everybody. And if the base is 1, you have a horizontal line. In other words, you don't have an exponential. So a has to be either between 0 and 1, which makes it decreasing, or larger than 1, which makes it increasing. These are some exponential properties, such as a to the power of 0 equals 1, and so on, that is available to you. So what happens when you're dealing with an exponential function? You have a horizontal asymptote, which is the x-axis, has the equation y equals 0, okay? There is no vertical asymptote, okay? There is no x-intercept, and there's a y-intercept of 0, 1. The domain, remember, the definition of a domain is possible values of x, all possible values of x. It covers from negative to positive infinity, and the range is from 0 to infinity. So when a is larger than 1, in this case, it's increasing. The limit of f of x as x approaches infinity is infinity, in other words, the first quadrant. And limit of f of x as x approaches minus infinity is 0, and that is the definition of a horizontal asymptote. If it's between 0 and 1, this one, then this is a decreasing or decay function. Limit of f of x as x approaches infinity is 0. And limit of f of x as x approaches negative infinity is positive infinity. Reminding you of some of the logarithmic properties. Remember, log x base b equals y means if you follow this arrow, b to the power of y equals x. Again, I'm reminding you of what you've seen in algebra, and therefore the general case creates the following properties. Log 1, any base, b is any base as long as it's not 1. It's either between 0 and 1 or larger than 1. Okay, remember, b must be positive and it can't be 1. It's 0, log b base b equals 1, and so on and so forth. Okay, these two refer to the fact that logarithmic functions and exponential functions are inverse of each other. So log b to the power of x of base b is x, or b to the power of log x base b is x. Product rule, log xy is log x plus log y. All of them have the same base b. Quotient rule, log of x over y is log x minus log y. All of them have base b. And power rule, log of x to the power of n is n log x, and they both have the same base b. Now, if we go with common log, that means the base is 10, and then we write y equals log x. We don't write the base, means 10 to the power of y equals x. And these properties that are general become specific for common log. Natural log, the base is e, so we write y equals ln x. That means the base is e. This is the meaning of it. Don't write it in that format, which means e to the power of y is x. And these are the properties. Again, general form, specific cases. And because logarithmic functions and exponential functions are inverse of each other, if you graph, for example, y equals e to the power of x and y equals ln x, they are symmetric with respect to the line y equals x. And it's the change of base formula, log x base b. You can write log x over log base log b. Any base, for example, a. Of course, we choose either common log, namely base 10, or natural log, base e. And as you can see here, this point has coordinates 1, 0. So if you go to the left of 1, it becomes the natural log becomes negative, to the right becomes positive. Okay, when we say to the left, between 0. So this is just the synopsis of one thing that was covered before this as a chapter in the text. And exponential and logarithmic equations, in short, you have the same base, you have the same exponent. For example, here, a to the power of x and a to the power of y are equal. Because we have the same base, we must have the same exponent. Over here, the same thing. And for logs, the same thing. So over here, a to the power of x, b to the power of x is the same. They have the same exponent. They have the same base. If x equals y, log x base a and log y base a are equal. Okay. And by the way, the base and the argument, x and y are called the argument. They must be positive. A simple interest, I equals PRT. Compound interest, A, P times 1 plus R over n to the power of nt. And this is compounded continuously. Future value, P equals to P sub 0 e to the power of kt, A equals P e to the power of RT. These are different ways of writing it depending on the text. Doubling time, the amount of time it takes for something, for population or investment to double in size. ln2 over k, it can be proved. And the effective rate of interest, A is P1 plus R over n to the power of RT, or E is 1 plus R over n to the power of n minus 1, or e to the power of r minus 1. This is just to remind you some of the stuff that came before this section. You don't have to worry about it too much, but it's there in case. Now let's actually get started with our section. 5.1, angles and their measurements. So we want to look at the following definitions. We want to look at the vertex. Here's the vertex. We want a ray, line, initial side, terminal side, positive angle, CCW, counterclockwise, negative angles, clockwise, standard position. So let's get started. Vertex, the vertex is the single point that is the common end point of the two rays forming an angle. Line, a geometrical object that is straight, has no thickness, and extends indefinitely in both sides. Ray, a ray is a part of a line that begins at a specific point, the endpoints or the vertex, and continues forever in one direction. In essence, you can think of it as a half line. Now, here's the vertex, here's the initial side, here's the terminal side, and counterclockwise, this way. Counterclockwise rotation is considered positive. So that's a positive angle. Initial side, when forming an angle, the initial side is the ray that remains fixed in its starting position. Terminal side, so this is the initial side, this is the terminal side. The terminal side is the ray that rotates from the initial side to form the angle. The direction of rotation determines if the angle is positive, that means counterclockwise, or if it's negative, that means clockwise. Standard position. An angle is placed in standard position when its vertex is at the origin of the coordinate plane. The initial side of the angle always lies on the positive x-axis. The terminal side rotates from the initial side. So take a look. So again, we have the initial side, we have the terminal side, and this one is obviously clockwise and therefore negative. This one counterclockwise and positive. And notice we've gone more than a complete revolution. So here's the rectangular coordinate system. Here's the positive side of the x-axis. So if the angle is along that, the initial side, we say theta is in standard position and theta is positive. Why is it positive? Because it's a CCW, counterclockwise. However, this one is in also a standard position, but look at this theta. This is a negative angle because it's in clockwise position. So pretty straightforward. So we wanted to look at some definitions to get us started. So a quick recap. When you have an angle where the initial side and the terminal side intersect or meet, it's the vertex. This is the initial side. This is the terminal side. Counterclockwise positive, clockwise is negative. And when the initial side is along the positive side of the x-axis, it is considered in standard position. All right, so let's look at quadrants, quadrantal angles, and take it from there. So, rectangular coordinate system, it gives us 4 parts. This is the first quadrant, where theta is between 0 and 90 degrees. This is considered 0 degrees, 90 degrees, 180 degrees, 270 degrees, go back to 0 or 360 degrees. So the first quadrant between 0 and 90 degrees, second one between 90 and 180, third one between 180 and 270, and the last one between 270 and 360 degrees. What about the angles that are on each side? In this case, positive side of the x-axis would be 0. Positive side of the y-axis would be 90 degrees. Negative side of the the x-axis would be 180 degrees. Negative side of y-axis would be 270 degrees. Going back here, 0 or 360 degrees. Those are considered quadrantal angles. So quadrantal angles have a terminal side that lies on the x-axis at 0 degrees or 180 degrees, or the y-axis at 90 or 270 degrees. In other words, take a look at them. So this one 0 or 360 degrees, this one 90 degrees, this one 180 degrees, and this one 270 degrees. So we are looking at some basic definitions. All right, we discussed the quadrants and now right angle, straight angle. So as we mentioned, theta lies in quadrant 2 here, right? The terminal side. This one in quadrant 4. This one, theta is a quadrantal angle because the terminal side is along the x or y axis. So if we go a complete revolution, one revolution counterclockwise is 360 degrees. Vertex, the initial side, the right angle, 1/4 of revolution counterclockwise, so 90 degrees, along the positive side of the y-axis. And this one, here's the initial side, here's the vertex, here's the terminal side, straight angle, 1/2 revolution counterclockwise or 180 degrees. So this is 90 degrees, this is 180 degrees. This is a right angle, this is a straight angle, and this is a complete revolution, 360 degrees. The terminal side and the initial side are at top of each other. All right, let's triangles. And remember, this is the initial side, this is the ray, and we want to go with a 45-degree angle, which means the initial side is here. Now, 45 degrees, we're going to go counterclockwise 45 degrees, and it gives us the initial side, the vertex, the terminal side, 45 degrees. Negative 90. Okay, so remember, this is counterclockwise is positive, this is clockwise, and it's negative. So we go clockwise 90 degrees. So this is negative 90, clockwise. This is the vertex, initial side, terminal side. Okay, as you can see, they're all in standard position. 225 degrees. So this is the initial side along the positive side of the x-axis. So we go this way, it's 180 degrees, and we have to go more by 45 degrees to get to 225 degrees, and it looks like that. So the initial side along the positive side of and the terminal side, 225. 405 degrees. As you can see, this is larger than 360 degrees. In other words, we start here and we go counterclockwise. We end up with 360 degrees, and we have to go more by how much? 360. This is so we go another 45 degrees, just like that. And as you can see, these two are considered coterminal. So what are coterminal angles? Coterminal angles are angles that share the same terminal side when drawn in standard position with their initial side along the positive x-axis. They may differ by an integer multiple of 360 degrees or 2 pi radians. Therefore, 445 degrees, which is 360 plus 45, it's coterminal with part A, namely 45 degrees. I'm going to convert between decimal and degree, minute, second, and so on. So again, counterclockwise revolution. One revolution is 360 degrees. 1 degree is 60 minutes. 1 minute is 60 seconds. So we have 1 prime. Over here, we have double prime. 1 prime means minutes. Double prime means seconds. Convert 40 degrees, 12 minutes, 5 seconds to a decimal in degrees, rounded to 4 decimals. So remember the relationship. 1 degree is 60 minutes. 1 minute is 60 seconds. Therefore, we are going to write 1 minute is 1/60th of a degree, and 1 second is 1/60th times 1/60th. That means 1/3600 degrees. So we are going to write this as 40 degrees plus 12 minutes plus 5 seconds first. And so 40 remains. 12 is 12 times 1/60, and 5 is 5/3600, or 5 times 1/3600. So this 40 remains. This one, 12 divided by 60 becomes 0.2, and this becomes 0.0014. So this means 40, and we are going to add those two 0.2014 degrees. And remember, they wanted the 4 decimals. This was exact. This one, we used 4 decimals. Now, let's go back. Convert 78.562 degrees to DMS, degrees, minutes, seconds form. That's the meaning of DMS. And round it to the nearest seconds. When we write it in that format, normally the seconds, they don't take decimals anymore. So having said that, so 78 is fine. We're going to work on this part. So this is 78 degrees plus this much in degrees times 60 minutes, because 1 degree is 60 minutes. So this portion we're going to multiply by 60. So never mind this, we're going to work on this. When we multiply 0.562 by 60, what number do we get? 33.72. So far it means 78 degrees, 33.72 minutes. This 33 is fine, but this one, 0.72 minutes, we're going to change it to seconds. How? You multiply 0.72 minutes by 60 seconds. So 78 remains. 33 minutes remains. This one, 0.72 minutes, we're going to multiply it by 60 because 1 minute is 60 seconds. So this one we're going to multiply by 60 and we call it seconds. So again, 78 remains, 33 remains, 0.72 times 60. When we do the math, this remains, this remains, this is 43.2. And as I mentioned, we just keep it as 43. Therefore, we're going to write 78 degrees, 33 minutes, 43 seconds. That's how we go from one format to the next. We changed from this format to degrees and vice versa. Both formats are handy. What is the definition of a radian? Radian definition. The measure of a central angle subtending an arc equal in length to the radius, which is about 60 degrees, about, so it's 57.3 degrees. 180 divided by pi. In other words, 1 radian, okay, gives us this arc. This arc has a length, and the length should be the same as the radius. That is the precise definition of a radian. So this is 1 radian. This is 1 radian. Okay, so regardless of the size of the radius, the size of the radius should be the same as the arc length. So having said that, find the length of an arc of a circle. Arc length is the length of the arc of a portion of a circle or part of the total circumference of a circle given the central angle theta, S equals R theta. Why is that? So theta and theta 1 or S over S1. So the relationship, the ratio between the two angles and between the two arcs are the same. Recall, circumference is 2 pi r, everybody. Circumference of a circle is 2 pi r. So the radius times 2 pi. What is 2 pi? 2 pi is the entire angle. It's 360 degrees in essence. It's a complete revolution, 2 pi radian. So if it's not a complete revolution, but it's some radians, for example, theta radians, okay, remember, S is 2 pi r, complete revolution. But if it's a portion of it, then 2 pi changes to theta because theta is a portion of that. So therefore, S equals R theta. So that's how we calculate S equals R theta. This is the justification for that. So having said that, as an example, we want to find the length of the arc of a circle of radius 4 subtended by a central angle of 0.5 radians. It's important to make sure the central angle, this is central angle, It's a central angle. Must be in radians. So S equals R theta. S equals R theta. What is R in this example? 4. What is theta? 0.5 radians. So 4 times 0.5, which makes it 2. And because this radius has the units in meters, the answer is the same unit in meters. So, a quick recap. Circumference of a circle, everybody knows, is 2 pi r. So, a portion of that circumference is called the arc length. Depends on the central angle. So, S equals R theta. All right, so convert degrees to radians and so forth. Definition: one revolution is 2 pi radians, or 360 degrees. Half of that is 180 degrees, or pi radians, or a straight angle. 1 degree, therefore, is pi over 180 radians. 1 radian is 180 over pi degrees. So one easy way to look at that, 180 degrees and pi radians are the same. So d over 180 must be the same as r over pi. If you go with this formula, any of them given, for example, degrees is given, you put it here, you find r. R is given, you put it here, you find d. Or, as I said, if it's a degree, you can multiply it by pi 1 over 180. If it's in radians, multiplied by 180 over pi to change. Common angles that we should know. Of course, 0 is 0. 30 degrees are pi over 6. 45 degrees pi over 4. 60 degrees is pi over 3. 90 degrees pi over 2. You can figure out the rest as well. These are in degrees or radians. Those are common. We should have seen them. We should have no problem with that. Okay. And of course, it goes further. For example, obviously 180 degrees is pi radians. 360 degrees is 2 pi radians, and so on. So I hope everybody remembers them. If you don't remember it from previous courses, make sure you get comfortable with them. As long as we remember 180 is pi, everything else should come to mind easily. All right, here's an example that we want to convert from degrees to radians, where A is 30 degrees, so on and so forth. We already know the answer, but just in case, the methodology is you either go with this, d over 180 is r over pi, or simply because you want to go from degrees to radians, times pi over 180. So 30 cancels out the 180 and you get pi over 6. Again, this is a common arc. We should know that, but I'm showing you the common arcs that were discussed in the previous page and how we arrive at it in case we have to. In this case, again, it's a common arc, but if you have any doubts, times pi radians over 180. 120 and 180, both of them are divisible by 60. We get 2/3. So 2 pi over 3 radians. It's the same as 60 degrees, but negative. I hope you know 60 degrees is pi over 3. So this is minus pi over 3. But again, times pi radians over 180. 60 cancels out the 180. So this becomes 3. Negative remains, and minus pi over 3 radians. What about this one? Another common arc, 104 and 180. You can just divide them. You get 1.815 radians because it's not a common arc. Now, if we want to go back, we want to convert from radians to degrees. Again, we can go back to this, okay, and replace the radians with r, with minus pi over 2 and find that, or just multiplied by 180 over pi. Needless to say, we know pi over 2 is 90 degrees, so this is negative. So minus pi over 2 times 180 over pi, pi's cancel each other, this one and this one. 180 divided by 2 is 90, so negative sign remains, minus 90 degrees. Okay, so as I mentioned, or d over 180 is minus pi over 2 over pi, do the job. For this one, obviously, pi cancel out, and then This cancels out, becomes 30 times 5, 150. Now 5 radians is not a common arc times 180 over pi. That's easier to do. And you get 900 over pi, or 284.48 degrees. Bear in mind, um, again, 1 degree is power 180 radians. 1 radian is 180 over pi. Might be easier to go this route, as I mentioned, because I just replace the d find r, replace the r find d.